Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about Newton versus Einstein. In Physics 107, we talk a lot about the system of physics that was developed by Isaac Newton in the second half of the 17th century, about 350 years ago, and we're still talking about Newtonian mechanics. Um, but as you probably know, another fellow came along. This is one Albert Einstein. He's a little bit younger than in the picture than perhaps you see him in popular imagination. But this is about the way Albert Einstein looked in the year 1905 when he was 26 years old, and when he published his theory of special relativity, which made some important modifications to the predictions of Newtonian mechanics. And like in this episode of What's the Big Idea, I'll tell you just a little bit about some of the ways in which Einstein uh, uh, theory of relativity modifies Newtonian mechanics, and why, even with those modifications, Newtonian mechanics is still very much worth talking about 350 years after it was first developed. So let's dig in. So, Newton's second law, N2, we've been writing as the acceleration of an object. And I'm going to leave out the vector signs now. We'll imagine that our object is moving in just one dimension, so we don't need any vector symbols. The acceleration of an object is just depends on the net force acting on that object divided by the mass of that object. And the acceleration of the object is, by definition, the derivative of the velocity with respect to time. So now let's consider a special case. Let's consider the case in which the net force is constant over time. And in that case, if F net is a constant, that means dv dt is a constant, which means the velocity is going to be a linear function of time. So I'm showing here the case where dv dt is a positive quantity, so the velocity is increasing linearly with time. And if we apply our force for a long period of time, the velocity keeps increasing linearly. There's nothing in Newtonian mechanics that puts any limit at all as to how high the velocity could go. If we push, even with a modest force, if we push long enough, you can get up to as high a velocity as you want, according to Newton's second law. And in 1905, Einstein came along with his theory of special relativity, which, if you've taken Physics 100, you've heard a lot about. And the special relativity literally says, not so fast, Isaac, not so fast. Einstein basically, a consequence of his theory of relativity is that Newton's second law, which we'll write as F net equals m times dv dt, that's the standard way of writing the second law, is not quite correct. Is not quite correct. The correct law, according to Einstein, is actually a bit messier to write down, but let me try. So one way to write down the sort of Einstein's modified version of the second law is that the net force is equal to the mass times the derivative with respect to time, not just of the velocity, but there's this additional term in here, this somewhat messy term, 1 over the square root of 1 minus v squared over c squared. That's the term, times the velocity. And for those of you who have taken Physics 100, this messy term with the square root here is typically given by the name of the Greek letter gamma. And in this expression, the quantity c that appears here is a constant that is equal to the speed of light, which, as you probably know, is a very high speed indeed of 3.0 times 10 to the eighth meters per second. So this is indeed a messier situation because even in the case of where the net force is constant, and if the net force is constant with Newton's version of the law, that means dVdt is a constant. And it was very easy to write down what v of t looks like. If you think about what's involved in taking the derivative of this function with respect to time, it gets quite messy. Um, but nonetheless, I can tell you what the result is. Um, but before I do that, let me just point out an important point. The important point is that we, in this course, in Physics 107, um, typically almost always deal with objects that are moving at speeds that, whoops, that are very small compared to the speed of light. So even a speeding rocket, a rocket on its way to Mars, for example, is traveling at a speed of something like 10 to the fourth meters per second. That's more than 4 orders of magnitude smaller than the speed of light. So this quantity here, v over c squared, when you take v over c, it's a very small number, 10 to the minus fourth or less. And then when you square it, it gets even smaller. And so gamma here, uh, this factor of 1 over the square root of 1 minus a very, very small number, is nearly just equal to the square root of 1. And so gamma itself ends up being very nearly equal to 1, and for the cases where speeds are slow. And in that case, you can pretty much ignore it, and if you ignore gamma, then you're back at Newton's version of the second law. So the bottom line is that if you're dealing with speeds that are small compared to the speed of light, the complication introduced by Einstein's relativity doesn't really have much of an effect at all. But if you do enter a realm in which the speeds begin to become comparable, to the speed of light, then you really have to take into account Einstein's modification. And let me just tell you, without deriving it, but tell you in the case of a constant force, but as objects begin to approach the speed of light, what does v of t look like in that case? So on this new graph here, first let me remind you whoops, I'll just draw the prediction of Newton's second law. Again, Newton's second law says that if you have a constant force, v of t just uh, changes linearly. And what the implication of Einstein's modification of Newton's second law is that at low speeds, at speeds small compared to the speed of light, Einstein's result exactly tracks what Newton's prediction was, but as you begin to approach the speed of light, Einstein's result says that the speed does not increase without limit. In fact, it asymptotically ends up approaching the speed of light c, but never quite getting there. So you push with a constant force, and at first things just uh, increase their velocity linearly, but then it begins to sort of roll off here. And the speed of light ends up being sort of this ultimate speed limit in the universe, according to Einstein's theory. And I should point out that we can do experiments, we can test. That's the true mark of whether a theory is correct or not, is you do experiments and you see how nature behaves. And in this case, these experiments are done all the time in particle accelerators, where particles move at speeds that are very fast. And those experiments are unequivocal. Einstein's theory of relativity correctly predicts the behavior of how the velocity functions as a function of time, and Newton's result in red here clearly fails the test. Was Newton wrong? Well, in a sense, he was wrong, but again, if you're limiting yourself to these velocities that are small compared to the speed of light, everything is fine. If you want to get to Mars, Newton's second law, it will really take you there. You don't need to know all that much about the theory of relativity to get to Mars. Is Einstein definitely right? Well, Einstein himself said that no amount of experimentation can ever prove a theory right. And it takes only one experiment to prove his theory wrong. And what that means is that, someday we may do an experiment and we may find out that there are realms in which, or ways in which the theory of relativity is not quite correct. But I have to say that at this point in time, Einstein's theory of relativity is looking pretty good. Uh, so that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.